All right. Hello, everybody, and welcome to today's live solve. So, before we introduce ourselves, you know what? I guess we can start with introducing ourselves. So, with me here, I have Leo. Leo is a junior based out of Seattle, and Leo has a lot of experience with the math competitions. He's been doing the AMC every year for a while now, and he achieved AMC DHR in seventh grade, which, in case you guys don't know, means he was in the top. What is it? 1% or 5% of
I,
participants?
I don't remember. Something like that.
Long story short, Leo is very, 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 very good at math. He's qualified for AME since ninth grade, which is also extremely impressive, and he's gotten second at his local UW Math Hour Olympiad twice. Outside of math, he enjoys playing on his high school frisbee team, and he coaches his middle school's frisbee team, and he's also the captain of his school's quiz bowl team. So he has talents even outside of math when it comes to school, and he enjoys biking as well as folding origami.
Hello, everyone. And I'm here with Samarth, who has been doing math competitions since fourth grade. He's qualified for Amy 3 times and Math League Nationals in fifth grade. So lots of experience in this specific math competition. Samarth is an officer for his school's Mu Alpha Theta and Chemistry Olympiad chapter. I recently realized Mu Alpha Theta is like Greek letters for math. So that's cool.
MAT. Yep.
Uh, he also actively participates in the math team at his school. He enjoys tutoring, reading, public speaking, and table tennis in his free time. So, warm welcome for Samarth.
Hello, everyone. Thank you. All
And
right.
now we want to hear from all of you. So, uh, please tell us, would you rather have later dawn or earlier dusk? And, oh, Bryant Lee, thank you for messaging chat relay. This is a good reminder. Uh, Everyone, do not tell us directly in Zoom. Actually, message chat relay, and your answers will appear down here on my screen and on Samarth's screen.
All right. So, just in case the question was a little bit confusing, basically what we're asking here is, do you guys enjoy the daylight saving system or not? Would you rather keep daylight savings and then gain that extra hour of daytime, or would you rather just do away with daylight savings and like enjoy the extra nighttime hours that come during winter? Okay. And it looks like we're actually decently split. It looks like there's a couple of people who it looks like we're pretty evenly split between people who want to keep daylight savings and people who don't. So, I guess for those of okay, and it seems like the consensus is the people who want longer night times just kind of want to sleep more. Leo, do you think that you're actually going to get any more sleep just because the nighttime lasts any longer?
I don't think so. I think, at least for me, the reason I stay up is not because I'm unable to sleep while the sun is up, because I have shades in my room. I think it's just my personal behavior. I think I could adjust my sleep schedule any way I want pretty much if I like school is not going to move itself, but I can move around as much as I want. What about you?
Me personally, I prefer longer nights. Like I actually don't particularly enjoy having to deal with this like having to deal with transitionary days in and out of daylight savings because I'm a nighttime person. Like my favorite time to walk is when it is pitch black outside and I can see the stars when I look up. And let's just say it's harder to do that when it's harder to do that when everything is pushed forward an hour and then like the sky ends up getting darker an hour later than you expect. So me personally, I'm not a huge fan of daylight savings. Yeah, also, I don't know if you guys knew this, but traffic accidents have like there's like a dramatic increase in traffic accidents the day daylight saving starts and the day daylight saving ends because of how messed up everybody's schedules and how because of how messed up everybody's schedule is because of the certain like shift in the amount of sleep they get. So
Hmm.
like even like on a macroscopic level, I feel like there's just not that many like benefits. Like this was a policy that was instated ages ago, and I don't particularly know why we keep doing it.
Maybe it'd be better if daylight savings time was 1 minute every day marching forward so that no one has the 1 hour shock. But I think there's also some potential drawbacks to that system.
Yeah, it'd be like a boiling the frog kind of situation. I feel like so. Yeah, and Krisher brings up a good point. there's nothing more annoying during daylight savings time than like having to adjust like your microwave clock and your oven clock. Because I know like when I'm getting ready for school, I rely on like those clocks. Generally, I don't have my phone on me all the time, so I'm gonna be like looking at my microwave clock or my oven clock in order to figure out like when I have to get ready for the bus. But sometimes if I like wake up really really early by accident, like before my alarm, it's kind of hard to tell what the time actually is because I have to remember whether or not I'm adjusting forward an hour or not.
Hmm. Personally, I solved that problem in my bathroom. There's a clock in the shower, and I honestly just did not change it for the entire daylight savings time. So for 6 months, it's been off by an hour, and it's finally back to correct. So I guess one option is just not do anything.
It's a broken clock is right half the year.
Hmm.
Hmm. All right. Well, it looks like we have a lot of potential. It looks like we have a lot of potential solutions to this problem, but unfortunately, or I guess fortunately, we are not actually here to talk about clocks today. Instead, we have something a lot more interesting to talk about. So, Leo, are you ready to get started with today's live solve?
Yeah, let's go.
All right, let's get into it. All right. So, our first question is question 1. Sanford is inspecting 10 gadgets, 2 of which are defective. He randomly chooses 5 of the gadgets to inspect. Sanford will only allow the batch to pass if none of those 5 gadgets are defective. What is the probability that the batch passes? Express your answer as a common fraction. All right, so when I'm looking at this problem, what we're trying to figure out, well, I guess my first thought process is like, what is the fraction I'm actually trying to figure out? And effectively, what it comes down to is it's the probability that we select 5 good, the probability that we select 5 good gadgets. Now, Leo, there are a couple of ways to calculate probabilities. What do you think is the best approach to take for this kind of problem?
Well, I think we should think of this as a chain of good luck, of 5 lucky outcomes in a row. So I guess just starting with the first lucky outcome, this first smiley face will be related to what is the probability that the first gadget Sanford picks up is not defective. So, well, this one's pretty easy, I think. There's 10 gadgets, 2 of which are defective. So it's just 8 out of 10, right?
Yes.
How about the next one? Do you want to figure out the next one?
Yeah, so if the first one was 8 out of 10, then now we've removed one good gadget. So the next gadget, there's a 7 out of 9 probability that that one is going to be good.
Why 9? Why not 10?
Because we've already eliminated one gadget from our batch of selectable gadgets when we selected our first good gadget. All right. And then so on and so forth. We have this like we end up with this like long-ish chain of and then 4 times 6. And then this ends up kind of being our probability chain of possible gadgets to select. And then when we do a little bit of math, we can cancel out a lot of these fractions, and then we get 5 times 4 over 10 times 9, which I think some people correctly said evaluated to 2 over 9. Right?
Yeah,
so
that seems right to me.
that seems good. Yeah. And that is in fact one way to solve the problem. There is also an alternative way to solve the problem, which is that if you think about it, this is also equal to this is also like because you can always express a probability as the number of favorable outcomes over the number of total outcomes. The number of favorable outcomes is the same as the number of ways you can select 5 good gadgets from our batch, which is equal to 8 choose 5. And then the number of total outcomes is equal to the number of ways you can select 5 gadgets from a batch of 10, which is equal to 10 choose 5. So this evaluates to 8 times 7 times 6 over 6. All that over 10 times 9 times 8 times 7 times 6, all over times 4 times 3 times 2. And then if you do a little bit of math here, you get, I know this is very messy, 8 times 7 over 9 times 2 times 7, which, yeah, again, 9 times 4 times 7, which again evaluates to 2 over 9. So either one of those approaches is a perfectly valid way to get the answer we want. All right, so are you ready to check the answer?
Yeah, let's do it.
All right. And it looks like we are correct. All right, on to the next problem. So,
Okay.
Leo, go ahead.
Yeah. A three-term arithmetic sequence with a common difference of 1 has the property that the sum of the numbers is equal to 2026 times the smallest number. What is the value of the smallest number in the sequence? Okay, so I see a problem like this. What I want to do first is assign a variable. Samarth, what variable do you think we should assign first?
No, I always like x. I think x is a very good standard variable to rely on for this kind of thing.
All right, let's do x. So let's let x represent, I guess, the first term in this arithmetic sequence. So then the other terms would be x plus 1, and x plus 2. Okay, where should we go from here?
All right. So from here, we know that the sum of the numbers is equal to 2026 times the smallest number. So from here, if we add up the numbers, the sum of these numbers is obviously 3x plus 3. And we know that this is equal to 2026 times the smallest number. So this is equal to 2026 times the smallest number. Now, which of the terms is going to be the smallest number?
It would be this one, x, because that's how we defined it.
Mm-hmm. And because the common difference is a positive number, which means that the terms are increasing as the sequence goes on. So from here we get that 2026x is equal to 3x plus 3, and then doing some very simple algebra, we get x is equal to 3 over 2023.
All right.
Are we ready to check?
Yeah, let's do it.
Yep.
Okay, yep. So there was an issue with the slides, but this is indeed the correct answer. We checked the answer.
The answer is in fact 3 over 2023. All right, on to the next problem. How many subsets of 3, 4, 5, 6, 7, 8 contain a pair of elements summing to 11? All right, so I guess my first thought might be that I'm just going to start counting subsets that sum directly to 11. But I have a feeling that might be a pretty inefficient way of actually going about the problem. Leo, do you have any other ideas?
Let's start with that idea and then see where it goes.
Okay. So, first things first. I guess first things first, I could probably just pick the set 3, 8. There's also 4, 7. And 5, 6. So those are all the 2-element ways I can sum to 11. Are there any 3-element sets that would where all of the elements together would sum to 11?
Yeah, we could take, well, actually, any of these plus any other element would work. Because we'd still have these two plus just something else kind of just chilling, not doing anything, but it still works.
It's true. So what I'm hearing is any superset of any of these 3 sets would in fact be a valid set because it would contain one of these 2 pairs. Okay, so then the question becomes, how many supersets are there of each of these sets? So for each of these sets, we have that there are the 2 elements that are given, and then we have 4 other elements to choose from in terms of what we add to the set. So that means that the number of supersets is going to be 2 to the 4 for each of these, or 16, because we can choose which of the other 4 elements we want to include. But this isn't the complete answer, because after all, the full set 3, 4, 5, 6, 7, 8 contains all 3 of these, but it's counted once in each of these, which means that we have a couple of sets here that are being overcounted. Leo, how do we deal with overcounted sets?
Well, what exactly would an overcount look like? Well, I think it's, for example, like 3, 4, 7, 8. Something that has 2 ways would be counted twice, because it would be counted by 3, 8 and adding 7, 4, and it would be like 4, 7 and then adding 3, 8. So we kind of need to subtract 1 for each superset of this, and also each superset of these 2, each superset of these 2, and each superset of these 2. But we're not quite there. But let's Let's calculate out what that would be.
All right, so we have 4 elements that are like a given in our set. For any one of these, for any like superset of 2 of these sets, we have 4 elements that are a given for the set, and then we have 2 more elements that are unknown quantities as to whether or not they're in the set. So each of these subsets corresponds to 4 supersets individually.
That makes sense. But we're not quite there. I guess, should we draw the Venn diagram here?
Yeah, let's draw the Venn diagram. So
Okay.
if we were to draw a Venn diagram of where, okay, let's have this top circle refer to the set of all supersets of 3, 8. And this represent the set of all supersets of 4, 7. And then this is the set of all supersets of 5, 6. Then we can see that what we've done is we've included in all the big circles, in each of these big circles, we have included we've counted everything in the big circles once. Now, each of these sets of 4 that we are including is, each of these sets of 4 that we include has, it basically represents one of these like intersections over here of 2 of the circles. So we've counted all of the big circles, once, and then we've subtracted all of the intersections once. All right. Or I guess if here, let's see if I can, yeah. How do I want to do this? Okay, so basically, we've counted all of our big circles once, and then we subtracted out all of our intersections once. But in case you haven't noticed, this very, very centermost like triangle in the middle of our Venn diagram has been counted once for each of our big circles, and then it's been removed once for each of our intersections. So currently this center piece has been counted exactly 0 times. So we have to add that term back in order to get our like final sum correctly. And the number of this final term corresponds directly to the superset of all 3 of these sets combined, which happens to be our whole set. So that just evaluates to 1. So our final answer ends up being 3 times 16 minus 3 times 4 plus 1. Which evaluates to, I
think
believe
37?
37. Yes, I think. All right, are we ready to check?
Yeah.
All right, let's go. I did see in chat that a lot of people were saying that the answer was 3. Just to clarify as to why that isn't the case, 3 would be the answer if it was if the question was asking how many subsets of this set can exist such that all elements sum to 11, like all elements inside sum to 11. But in this case, because we're including a lot of sets where there can be like redundant elements in the set, we have to include all possible supersets of all of these sets. All right, are we ready to move on?
Yeah.
All right, let's go.
All right, do you want to read this one out?
Yeah, sure. 2 circles are concentric with radii of 3 and 2, and they share center O. Point P is equidistant from both circles, and line L is drawn so that L is perpendicular to the line segment OP. In addition, line L passes through O, and it intersects the larger circle at point Q. What is PQ squared? Oh boy.
Okay, let's draw a diagram.
Yeah. Oh, by the way, Hank, concentric means that the circles are inside of each other. Or I guess more specifically that they share a center. Okay, so radii of 3 and 2. So we have 3, and we have, that's the 3, this is a 2. Okay, 2. Point P is equidistant from both circles, and line L is drawn. Okay, then we will take point P to be over here, and L.
So is it something like this? Am I drawing this right?
Um, it says L passes through O, and
Oh.
I think it's something like this, where yeah, P is equidistant from both circles. So P is in the center of the two somewhere over here. And
Mm-hmm.
then we have that, yeah, okay, L is drawn so it's perpendicular to, oh, wait.
But it passes through O. So it's like this?
It passes through O, but it's
Perpendicular
perpendicular.
to OP?
Yeah,
Okay. So it's like this. And this is OP, and this is L, which
yeah,
is perpendicular?
I think
Okay.
you're right. Yeah.
Huh.
So it's like this. Okay. O
Oh, and then Q.
passes
So
through
there's
O.
2 points Q that could work. Let's say it's this one.
Okay, yeah. So,
Like that?
sorry, this is a bit messy, but this is our diagram, guys. We have, um, yeah, this is our diagram. We have our circles of radius 2 and 3. We have our center O, and then we have our point P, which is in the middle of, we have point P, which is in the middle of the 2 and 3 radius circles, and then Q, which is up top here. And then our goal is to find the value of
PQ
this,
squared.
PQ squared. Now, this seems like a doozy, right? But the first thing I notice is that we have that our line L here is perpendicular to OP, which immediately means that we have a right angle. More specifically, that we have a right angle right over here. Keep in mind, yeah, where this is OP and this is OQ. Now, the really useful thing about right angles is that because we're trying to find the side length of the hypotenuse squared, all we have to do is add up the squares of the two side lengths over here. So all we have to do is figure out the length of OP and the length of OQ. Now, the length of OQ is pretty obviously the distance between the center of the bigger circle and a point on the bigger circle, which is by definition the radius. So we know that OQ is equal to 3 squared, which is 9. Now all that remains is to find the length of OP. We know that P is equidistant to 2 and 3, the circles of radius 2 and 3, so it's going to sit directly in the middle of those two, which means that its distance is going to be 2.5, or 5 over 2, which means that OP squared is equal to 5 over 2 squared, equals 25 over 4. Or if you want to do, yeah, 25 over 4, or in decimal notation, this would be 6.25. Then, if we add these two values together, we get that PQ squared is equal to 15.25, which is equal to 61 over 4.
Sounds good to me.
All right, we're ready to check?
Yeah, let's look.
All right.
We're right.
Let's go.
Good.
Okay, Leah, do you want to take this one?
Sure. Frankie has a 7-digit password that, I'm hiding behind this. One sec. Okay. Frankie has a 7-digit password that he has forgotten. However, he knows that all 7 digits are positive and that the sum of the digits is a multiple of 3, and that the sum of the squares of the digits is 32. Given this information, Frankie randomly guesses a number that meets these requirements. What is the probability that he guesses his password correct? Okay. When I see this problem, I wanna just start trying stuff. So the sum of the squares of the digits is 32. That means that none of the digits can be 6 or more. Okay, so yeah, none of them are 6. One of them could be 5. Let's see what that would look like. If one of them's 5, then it would be 5 squared plus, I guess, a bunch of 1 squareds. We'll do 6 of those so that there's 7 digits. And that would be 31.
1.
Right? So that doesn't exactly work. Okay, so we're not going to have 5s in this code either.
Yeah. By the
Then
way,
if
the
it
reason it
once-
can't be that is because if we were to add a 4, then we would end up going over. But if we don't add a 4, then we end up, like if we have a 2, then it'd be 5 squared plus 4 plus some number that'll end up being greater than 31. And then if we don't have any 4s or above, then we end up under.
Yeah, it would be too low. Okay, now it's ones, twos, threes, and fours. I feel like the most important. I think like going from the top makes sense, and then kind of filling in the gaps. But so, do you see like a creative way to do this problem, or just try it?
I think for now, let's try brute forcing it for a little bit and see if we can come up with a cooler solution down the road.
Okay. Let's say one of the digits is 4. Uh, so that contributes 16. Now, if we had another that's a 4, then we've already kind of used up all of our 32 squared allowance. And the rest of them, like there's no space left, and they all have to be positive. So that's not going to work. If we've got a 4, then the next one's got to be 3, 2, or 1. Or the rest of them have to be 3, 2, or 1. Okay, let's put a 3 here. And a 9. So that's 25 now. If we put another 3, then we would also go over our allowance of 32. So that's not going to work. We could put a 2. Now we're at 29. And I think we've already also gone over. Because now we're at 29. And we only have... All right, we have 4 more to fill in. But even if they were all 1s, we would go to 33. And we only have 32 allowance. So a 2 again is not going to work. Question is, could we do all 1s at this point? And I think we would come up short in this case. So I'm thinking 4-3 is a losing combination. Okay, what about 4-2? 4-2. Well, here's the thing. If 4-3 is a losing combination, the rest of them would all have to be 2s and 1s. Let's see.
Okay, so if we look at the 4-2 case, then our squares are 16. Sorry, my thing is kind of a mess right now. Let me just clean up my workspace a little bit. All right. If we start out with the 4 case, then we have 16 as our running sum. If we were to add a 2 after that, we would end up at 20. And then another 2 gets us... Oh, that's what I meant to write. Another 2 gets us 24. And then another 2 gets us 28. And then another 2 gets us 32. So with this many 2s, we would end up right at our allowance. But this only has 5 digits, which means that it isn't enough. So that means that we could not have a 2 at the end right over here. So instead, if we leave off if we just start with our 4 and then 3 2s, then our running sum ends up being 28, and then we have 4 digits left to get 32.
Yeah, I think we have 3 digits left. Is that right? It's 4, 2, 2, 2.
Yeah, but we have 7 digits. So we've used up 4 already, and we have 3.
Oh, yeah.
Yeah. So if we add another 2, then we end up going over. But if we add only 1s, then if we add only 1s, then we end up short. So it looks like 4-2 is also a failed attempt.
And if we just did 4 and then a bunch of 1s, that's
Then
not
we would
going to
also
work
be
either.
short.
We're going to be short
That
again.
means that none of those work. So that means we don't have any 4s either. Now we can get to the 3s. So if we start out with 3, if we started with a 3, that gives us 9. If we started with, so if we have a 3, then that gives our son 9. Another 3 would get us to 18. And then let's say we did one more 3. That would get us to 27. And now we have 4 digits we have to get 4 digits that would sum to, we'd have to get 4 digits that sum to 5. So we've already seen before that 4 digits summing to 5 is impossible. So this number can't be a 3. If it were a 2, then we would have our running sum at 22. So we would need 10 digits. We need a sum of 10 from 4 digits. And I think this one is actually possible, because then we could do 3 3 2 2 1 1. Or sorry, 3 3 2 2 2 1 1. And then we get 18 plus 16 plus... No, wait.
Wait, I think this is right. I think you're right. Wait.
Oh, yeah,
Three,
wait, that's
2, 2,
18
2, 1,
plus,
1.
yeah. 18 plus 4 plus 4 plus 16 plus. Oh, I added one extra. That's why. I added an extra 2. 1, 1. Yeah. And then we get 18 plus 12 plus 2, which does actually add to 32. So this is one possible combination. Um, and then from here, actually, we can see that I don't think there are any other combinations of numbers that'll end up working. Because if we were to, like basically every valid set of numbers that looks like this has to, is like the only like way that we could actually get numbers that meet this criteria. Because if we were to like use n 1 less 3, then we would always end up coming short. And if we were to increase the value of any of these numbers, we would end up going over. It's kind of hard to verify, but it's kind of hard to like you'd have to verify it yourself. But like we basically need to use like only permutations of this sequence would actually end up getting us to getting our sums to be equal to 32 of the squares. Okay, so now that we have this, Leo, how do you think we'd go about getting the probability?
I think we should use. I think we should figure out how many different codes are permutations of this, and then Frankie's going to guess one at random, and the answer is just one at random. So we're going to do 1 divided by the number of ways we can permute these, right?
Mm-hmm.
Okay, so that would be 1, 2, 3, 4, 5, 6, 7 of these. So 7 factorial. But not quite, because these 3's are indistinguishable, these 2's are indistinguishable, same with these 1's. So we're going to divide by 2 factorial times 3 factorial times 2 factorial, because there are 2 3's, 3 2's, and 2 1's. Okay, now what are we going to get here?
After doing a lot of simplification, we get that this number ends up evaluating to 210. So that means our answer should also be 1 over 210.
Okay. Oh yeah, I believe it. Okay, let's go for it.
All right, let's check. Perfect. All right, let's move on. Okay. All right, quadratic polynomials p of x and q of x both have leading coefficient 1. Given that p of 0 plus q of 0 is 4, and p of 1 plus q of 1 is 7, what is p of 2 plus q of 2? Whenever I do problems like this, my first step is always just write out p of x and q of x as like actual polynomials. So I'm going to say p of x is equal to ax squared plus bx plus c, and I'm going to say like q of x is equal to dx squared plus ex plus f. Yeah, okay, whatever. When I plug in p of 0 and q of 0, I get that when I plug x equals 0 into both of these, the ax, like the x squared and the x terms kind of disappear. So we get that basically c plus f is equal to 4. And then when I plug in x equals 1 to both of these, I get that a plus b plus c plus d plus e plus f is equal to 7. And then our goal is to figure out what is p of 2 plus q of 2. So plugging those coefficients in, we are solving for the value of 4a plus b plus c, 4a plus 2b plus c, plus 4d plus 2e plus f. But we have some hints here already. We know that, but we already have some clues. We already know that c plus f is equal to 4. And then using that information, we can actually conclude that a plus b plus d plus e has to be equal to 3. So we, a plus b plus d plus e has to be equal to 3. And, and then one more really big piece of information is that the leading coefficient is 1. So actually, I've been wasting some space. We can just kind of get rid of the a and the d here. So that means that we can substitute a and d are 1. And then that gives us 1 plus b plus 1 plus e is equal to 3, or b plus e 1. All right. Okay, I'm going to assume that I haven't made any major mistakes here yet. So from here, we get that, yeah, assuming I haven't made any algebraic errors. Now our answer to this problem just ends up being 4 plus 2 times b plus e plus c plus f, which we've already figured out is equal to 4 plus 2 times 1 plus 4. So that should in total evaluate to, oh, okay, I'm getting 10, but some people aren't agreeing with me.
I got 10 also, but I'm not exactly sure. We could run through it again. Let's see.
Let's run through it again. Yeah, I think my algebra at the beginning kind of messed me up.
I definitely get the c plus f equals 4 part at the beginning. That makes sense to me because yeah, from here you just use c plus f. That seems right. And then if we plug in x equals 1 here, I get 1 plus b plus c plus 1 plus e plus f equals 7. And then I subtract 2 from both sides. I get b plus c plus e plus f equals 5, and c plus f is 4. So I get those equal 1 also.
Mm-hmm.
Huh. Oh, maybe it's this x squared part? No, that seems right. Oh, I think I see what happened here. It should have, instead of 4, it should have been 8, I think. Because it's x squared plus x squared.
Oh, yeah. 2 times 4. Okay, yeah. And then that gets us 14. All right. So that gets us that our final answer is 14. And then two, just to double check. Yeah, I think that should be right. All right, are you ready to check?
Let's do it.
All right, and yes, I know. We kind of went through this kind of weirdly, so we will try to come back to it later. But yeah, like long story short, basically you have your equations for the quadratics over here, and then you're basically just plugging in x equals 0 and x equals 1 into both, and then using that to solve for the coefficients. And then once you solve for the coefficients, you can directly compute p of 2 plus q of 2. All right, and on to the next one. Okay, Leo, do you want to take this one?
Sure. How many positive integers less than or equal to 1,000 have a prime factorization of the form p to the k times q for distinct prime numbers p, k, and q, such that p plus k equals q? This one seemed like this would be quite difficult until I looked at this last equation, which is very sus, because prime numbers don't usually have this property, because most prime numbers are odd. So, as you guys know, an odd number plus an odd number equals an even number. And I don't know of any. I do know of one even prime though, because it's not going to be just odd primes in here. Anyway, I'm trying to say either p or k, one of them is 2. And I'm not saying the number 1 is 2. I'm just saying one of these 2 primes is going to be 2. And it's not going to be q because 1 plus 1 equals 2 doesn't work because 1 is not prime. Okay, now we've got something in the form 2 to the k times q, or, and I'll do this one on the other side. We can kind of take this in 2 cases. We can do p to the 2 times q. And there's a little bit more of a restriction here, actually, which is that these 2 primes have to be separated by 2. So either, in this case, 2 to the k times k plus 2, and in the other case, you see what I'm saying here?
Mm-hmm.
And it also has to be primes. So we should also keep track of what the twin primes we might want to consider are. Okay, what are some good twin primes, Samarth?
All right, just kind of going off the top of my head, we got 35, we got 5, 7, we got 11, 13, and we have 17, 19. Those should be more than enough. Like, well, way, way more than we need for this problem.
Okay, I'm satisfied with these.
All right. So if we just kind of start, like now we have our twin primes. These are the only possible values that we can start plugging into our pairs for each of these. And then from here, it just suffices to double check whether or not these, like which of these values ends up staying under 1,000. So for 3 comma 5, 2 to the 3 times 5 is just 40. So this one works. We have that 3 squared times 5 is 45. So this works. We have that 2 to the 5 times 7 equals 32 times 7, 224. Or either way, it is definitely
something under 1,000.
Yeah, something under 1,000. And then we have 5 squared times 7 is 175, which is also under 1,000. And then for 11, 13, 2 to the 11. Well, I know 2 to the 10 is 1024, so this is definitely over 1,000.
I know 2 to the 11 is 2048, like the game.
And then 11 squared times 13. I know 11 and 13 are both greater than 10, so this is also going to be over 1,000 because we're going to be multiplying 3 numbers that are all bigger than 10. So this means that the only solutions to our problem are these 4 up here, which means that our answer should just be 4.
Seems good to me. That was easier than I expected.
All right, let's check it out.
Hmm.
Voila. All right, on to the next one. Oh boy.
Uh-oh.
I don't like how many numbers there are. Okay, let's take a look though. Given that x and y are real numbers that satisfy the equations x to the 4th plus y to the 4th is 25 over 8, and x squared minus 2 squared plus y squared minus 2 squared is 25 over 8, what is the square of the greatest possible value of x? So basically, we are looking for x, the greatest possible value of, whatever the greatest possible value of x squared. Whatever that value is squared. Which isn't necessarily just the greatest possible value of x squared, by the way. So we are still going to have to double check that. But for now, let's just take a look. We have that x to the 4th plus y to the blah, and then blah. Okay, so I guess first things first, let's see if we can get any information out of what these values might actually be. So first things first, let's expand out this equation here. So x squared minus 2 squared is equal to x to the 4th minus 4x squared plus 4. And then y squared minus 2 squared is equal to y to the 4th minus 4y squared plus 4. Now, we have that both of these equations are equal to 25 over 8, which means that this is equal to, so we have like this, here, let's do it this way. We have that let me just okay, whatever. I'm going to rewrite it. We have that x squared plus x squared minus 4x, x to the 4th minus 4x squared plus 4 plus y to the 4th minus 4y squared plus 4. It all is equal to x to the 4th plus y to the 4th, which gives us negative 4x squared minus 4y squared plus 8 is equal to 0, or x squared plus y squared is equal to 2. Yes. Okay. So from that really, really big equation, we have gotten this. Which this looks really familiar because this is just the equation for the unit circle. This is just the equation for the circle centered at the origin with radius 2. So now we know that the set of basically our solutions to the above equation is just equal to the set of all numbers where x squared plus y squared is equal to 2. Leo, on this circle, what is the greatest possible value of x?
Okay, I got you. If we've got this circle, the most important part is off the diagram. One sec. If we've got this unit circle, The furthest most point for x is going to be when y is equal to 0, specifically the positive one. It's going to be this point right here. So with y equals 0, let's kind of just cancel that from the equation. We're going to have x squared equals 2 at this point right here with this value. So I think the answer is 2 here.
I also agree the answer is 2. Because specifically in this case, I think that x would be equal to square root of 2 as the greatest possible value of x, and then x squared would just be equal to 2. All right, are we ready to check it out?
Looks good.
All right. Oh my.
Okay, something went wrong. Okay, let's go back and check our work.
Yeah, I agree. Let's go back and check our work. Okay, we have our two equations that are equal to each other. So,
I can't
oh,
see
you know what it
immediately.
is? We forgot to
What is it?
actually check. We forgot to actually make sure that x to the fourth plus y to the fourth is equal to 25 over 8.
Huh. Okay, so it's not exactly though, because in this case that would be like x to the fourth would be 4, and y to the fourth would be 0, and that's
Yeah.
not exactly right. Huh. But then how were we even like allowed to get that option there?
Oh, it's because we were only solving for values. We were solving for like intersect. We were solving for just, I guess, making sure that these two equations were equal. But like that's the set of all. Oh yeah. So we solved for the set of all points where these two equations evaluate to the same thing. So then now we just have to figure out which one of them corresponds to the sum actually being 25 over 8. So now we have that x squared plus y squared equals 2, and then x to the fourth plus y to the fourth equals 25 over 8. And then now we just have to, yeah, and then now we just have to figure out what the actual value of x ends up being.
Okay. So maybe we square both sides of this x squared plus y squared equation and then subtract off. I don't know if that would really help though.
Hmm.
No, yeah, that doesn't seem right.
I think here it just kind of comes down to doing some substitution. So we could say x squared is equal to 2 minus y squared. And then, yeah, x squared is equal to 2 minus y squared. And then we get x to the fourth plus, sorry, no, we want 2 minus y squared plus y to the fourth equals 25 over 8. Or I guess if we're solving for x, let's do y as a variable of x is equal to x squared. And then we get x to the fourth plus 2 minus x squared. This is equal to y squared, so this squared is equal to 25 over 8. And then we expand, and we get x to the fourth plus, and this is equal to x to the fourth minus 4x squared plus 4 is equal to 25 over 8. And then we get 2x to the fourth minus 4x squared. And then this is minus, okay, so 32, yeah, minus 7 over 8. Or x to the fourth minus 2x squared minus 7 over 16. And then from here, I think, yeah, and then we can just do quadratic formula. So 2 plus minus square root of, oh, this is a doozy, 4 plus 7 squared. Nope, not 7 squared. That's 28 over 16. All this over 2. So 2 plus minus 64, 84.
People are pointing out in chat that it did say express your answer as a common fraction,
That
which
is
is a good,
true.
which is a good point.
And hmm.
Wait, what do you have there? Do you have 4 plus 7 over 4?
Yeah. Let's go back and verify really quickly. And then we have this. And then we should just be able to solve the quadratic. 2x to 4.
Question in chat from Hank. Why can you use the quadratic formula if the exponents are 4, 2, and 0? Doesn't it have to be 2, 1, and 0?
4, 2, and... Okay, I don't see where the 0 is. Specifically
like the constant term.
Oh, the constant term. Okay, yeah. The quadratic formula, like the quadratic formula, what it actually says is that if you have a quadratic of the form ax squared plus bx plus c, then the solutions to this equation are of the form negative b plus minus square root of b squared minus 4ac, all of this over 2a. So actually, you don't need the the leading coefficient of your quadratic to be equal to 1. It's just we generally like to have the leading coefficient be 1 because then we don't have to do really annoying math with the fraction denominator. But
I think they're not. Did I say coefficient? I meant to say that the exponent. I think the answer they're looking for is we're not doing when we do this quadratic formula. We're not actually doing like x to the fourth, x squared,
yeah.
x to the 0. We're actually doing something, and I saw someone else suggest this in chat, which is set z equals x squared, and then we're doing z squared, z to the 0, and then we're doing a quadratic in z, if that makes sense.
I probably should have explained that. Yeah. So what I was trying to do here actually is I was trying to solve for like the values of x squared that satisfy this, and then I was solving for the values of x squared that satisfy this, and then that's what I was actually going for in terms of my solution. Unless did I sub 32 minus 25 is 7. Let me go back and check my math really quickly. 25 over 8, and then all right, it seems like we're overcomplicating it. So why don't we try and go back to like scoring this equation to see what we get. So, oh yeah, I see what it is. So we can just go back and use these two equations again. So if we square this equation, we get x to the fourth plus 2x squared y squared plus y to the fourth is equal to 4. But we also have that x to the fourth plus y to the fourth is equal to 25 over 8. So this gets us a 2x squared y squared is equal to 2x squared y squared is equal to 4 minus 25 over 8, which is 7 over 8. And then that gets us x squared y squared is equal to 7 over 16. And I believe when we... Okay, so we have that x squared plus y squared is equal to 2, and then x squared y squared is equal to 7 over 16. So if I let a equal x squared, then I got a plus b equals 2, ab equals 7 over 16. So then I let, okay, and then I let a equal 7 over 16 times 1 over b, and then I get a, I guess, b over 1 over 16 times 7 over 16 times 1 over a. And then I get a plus 7 over 16 times 1 over a equals 2. Or a squared minus 2a plus 7 over... Oh, there it is. I think I dropped a minus sign somewhere.
I didn't catch it.
Okay. And then this is where this is equal to 0. And then the solutions to this are a equals 2 plus minus square root of 4 minus 7 over 16 all over 2. This should give us what we want. Okay, and then 4 minus 7 over 16 is
Like 50.
oh, sorry, 4 times, sorry, 7 over 4. And then this gives us 2 plus
9
minus
over 16.
9 over, 2 plus minus 9 over 4 all over 2. So 2 plus minus 3 over 2 all over 2, the greatest value of which is 7 over 4. And then we have that a is equal to 7 over 4, but a was also equal to x squared.
Mm-hmm.
And that's where we're equal 7 over 4.
Okay, that makes sense. I got lost
All right,
there.
sorry about that, guys. I think we confused ourselves with our algebra, and then we kind of confused ourselves with our algebra. So that took a little bit longer than it should have. But yeah, basically, to get the solution, what you do is you take these two equations and you use them to figure out that x squared plus y squared is equal to 2. And then from there, if you'd done your math correctly, then you would have gotten this quadratic with a minus sign in the middle, and then that would have given you x equals 7 over 4. Sorry about that, guys. All right, so just to recap, let's go over the process again. We have that x to the 4th plus y to the 4th 20 equals 25 over 8. And we have that x squared minus 2 squared plus y squared minus 2 squared equals 25 over 8. All right, so to solve this problem, first things first, what we do is since we notice that since these two equations are equal, we can expand out this term over here to get x to the 4th minus 4x squared plus 4 plus y to the 4th minus 4y squared plus 4 equals x to the 4th plus y to the 4th. This gives us negative 4x squared negative 4x squared minus 4y squared plus 8 equals 0, which gives us that x squared plus y squared is equal to 2. Now from here, keep in mind that x to the 4th plus y to the 4th is still equal to 25 over 8. So what we can do is we can square this equation, and we can get x to the 4th plus 2x squared y squared plus y to the 4th is equal to 4, because we can just square both sides of this equation. But we can use the fact that we have this sum over here to get that 25 over 8 plus 2x squared y squared is equal to 4. And this gives us that 2x squared y squared is equal to 4 minus 25 over 8, or 7 over 8, which means that x squared y squared is equal to 7 over 16. So now we have that if we let a equal x squared and b equal y squared, we just have that a plus b is equal to 2, and ab is equal to 7 over 16. So as you all know, what we can do is we can use this to solve for a and b using a quadratic equation where we let b equal 7 over 16a, and then we get a plus 7 over 16 times 1 over a equals a plus 7 over 16 times 1 over a is equal to 2, or a squared minus 2a plus 7 over 16 is equal to 0. And then when we use the quadratic equation on this, we get that a is equal to 2 plus or minus square root of 4 minus 7 over 4 all over 2, which is equal to, and then 4 minus 7 over 4 is equal to 9 over 4. So this is equal to 2 plus minus 3 over 2, all over 2. So then we get that the maximum possible value of a is 7 over 4. And since a was equal to x squared, this gives us x squared is equal to 7 over 4.
Okay, good. Hopefully that clears it up for people. Definitely cleared it up for me, so.
All right, and unfortunately, we have run out of time for the live solve, so this is the last question we got to go over. Yeah, it was definitely not a very easy problem. It probably would have been easier if we didn't confuse ourselves with a lot of algebra the first time, but there you go.
Yeah, so tune in next time.
Yeah, thank you so much for coming to the live solve. We hope you learned something, or at the very least that you got to practice solving these problems again, and that you were able to enjoy it. As for the next ones, I mean, this is the 2026 Math League Sprint Round, so you should be able to access the questions online if you go searching for them. So I hope you all have fun. I hope everyone continues to do comp math, and thank you all so much for tuning in. Bye-bye.
Bye, everyone.